Chapter 8, Part 3 of the exam. I'm sorry, Chapter 8, Part 3 of the PowerPoint. We're starting with the more reactions to cover. These are all additional reactions. And basically, what's important for you is to be able to count the number of electrons needed for the new bonds and be able to monitor and see how these electrons are being, transferred to like one carbon formation of a bond with the electrophile. Like for the other reactions that you had, when the electrophile comes in, since electrophile doesn't bring any electrons, and there is a need for pair of electrons for electrophile to attach to one of these carbons. And let's say if the electrophile is going to form bond with one of these carbons, then just going from electron rich to electron poor, then pair of electrons that we have here from pi bond is going to be consumed. The other carbon will take the plus charge. And then you bring the nucleophile. So just being able to understand this part, that if you don't have pair of electron, there is no bond. And pi bond is weaker than the sigma bond, or if you have a carbon-carbon double bond, you have pi bond and sigma bond. When you break the pi bond, basically both carbons are going to have electron deficiency. Then you have to make two new sigma bonds in order to satisfy each carbon with the octet rule. So if your nucleophile brings a plus charge, it's going to cancel the charge from the carbocation with the negative charge from nucleophile with the plus charge from carbocation. If the nucleophile doesn't have plus charge, then it's going to be like neutral, like water or alcohol. Then the plus charge needs to be removed on additional step. So it is a follow-up step if the nucleophile is a neutral nucleophile. Addition of carbenes to CC double bond. So if you have a CC double bond, you bring in carbene. First of all, you want to know what is carbene. A carbene has pair of unshared electrons. Okay, carbene has pair of unshared electron, is like a CH2, but with the pair of unshared electrons. You have one pair of electron coming from carbene, one pair of electron from carbene, and then you have one pair of electron from pi bond. So you already have two pairs of electron for formation of the two sigma bonds. So carbene brings pair of electron, then it says that you don't have to bring a nucleophile later. So you get the pi bond from a pi bond from the carbon-carbon double bond as one pair of electron, and the pair of electron from carbene, a second pair of electron, and you end up with the two sigma bonds that you're adding here. So with the two sigma bonds, it's going to form carbon-carbon double bond, and you're adding carbon to these two as a bridge is going to make it like a cyclopropane. You're breaking the pi bond, you are bringing a carbene. So if you have, just going to put the blue color here, and then you have carbene. The pair of electron from the carbene is going to come and form bond with the one of these carbon, and then the pi bond will form the second bond. So we have the only bond that is left from CC double bond is the sigma bond. So these blue color bonds, those are the new bonds that are formed, and you end up with the cyclopropane is a new ring that is a formation of a ring, is a 3-member ring. Now the question is, how would you prepare carbene? So basically, just like before, how did you prepare the strong electrophile for bromination or for the electrophile, like if it was a H plus, or if you were adding bromine, like a Br plus first and then the Br minus. Now, what is carbene and how do you prepare carbene? Carbene is very unstable because carbon has only two bonds, one pair of unshared electrons, is not octosatisfied, it's missing two electrons, it's missing two bonds. So it's very miserable. So there's no stability. So you cannot, you don't have a container of carbene to open and pour some carbene to carbon-carbon double bond. So carbene has to be synthesized or prepared in the inside the reaction mixture. So if you have the diazomethane, so when you have like a diazomethane, like a release of N2, which is an exothermic process, is going to leave the carbene left out. So you have to have the diazomethane. And then when you have your diazomethane, you have two resonances. And the N2 is the formation of N2 is very unique reaction. Like when you have like dynamite working, basically N2 gas forms because N2 is a carbon-carbon triple bond. And with the carbon-carbon triple bond that is forming, I'm sorry, nitrogen-nitrogen triple bond. I'm sorry, I mixed that. So is a nitrogen-nitrogen triple bond for N2 gas, and triple bond forms, a lot of energy is being released. So it's highly exothermic, and highly exothermic reaction is going to be a spontaneous reaction. So formation of the N2 gas is going to be driving force for this reaction to prepare carbene. And when you have carbene, pair of electron from carbene plus pair of electron from the pi bond, from the carbon-carbon double bond, is going to be consumed to prepare the cyclopropane. So one concern is how the mechanism is going to be, or where are the electrons or logistics, and being able to track the bonds and electrons from CC double bond going to a cyclopropane. And second concern is how do you bring carbene, or how do you prepare carbene? One of the method is to use the diazomethane. Diazomethane is the N2CH2. So you prepare the you use diazomethane as a source for carbene. Another source for the for formation of the carbene is to use the Simmons-Smith reaction. In the Simmons-Smith reaction, you have the iodomethyl zinc iodide. Iodomethyl zinc iodide is going to give you zinc iodide as the byproduct. Again, you get like the zinc iodide, which is very stable, leaving this molecule. So this molecule, just like diazomethane, is not very stable molecule. So zinc iodide would leave as a stable product, and then it would produce the CH2 carbene. So when you have your carbene, then it's going to form the cyclopropane with the CC double bond. As long as you know the reagent, you don't need to know the mechanism for addition or preparation of the carbene to carbon-carbon double bond. The alpha elimination reaction. In the alpha elimination reaction, in this case, you start with the bromoform or like chloroform with a strong base. You are going to remove one of these Br, which is basically losing of the Br with the pair of electrons, and formation of the carbene, but is a dibromocarbene. Dibromocarbene, when the triangle or the cyclopropane forms here, is going to have two bromine attached to it. So it's going to be dibromo cyclopropane that is going to form. So that's for the alpha elimination. Again, just know the reagents. Mechanism for addition of the carbene is not a concern. If you have a trans product, a trans reactant of alkene, the product is going to be trans. And if you have cis, it's going to be cis. Just know the reagents that you have for the alpha elimination. It's going to be bromoform. For alpha elimination, you have bromoform, potassium hydroxide, water that is going to generate the dibromo carbene, and then zinc iodide with zinc and copper 1 chloride. Mixture of all three of them is going to give you also carbene here. This reagent, just know the reagents. And then the final product is formation or addition of a cyclopropane. Formation of cyclopropane or addition of cyclopropane. Formation of epoxide or epoxidation. We did talk about this proxy acid already. And epoxidation, meaning formation of epoxide. What is epoxide? Epoxide is a triangle or a three-member ring, 2 carbon, 1 oxygen. This is like epoxide. The other name for it is ethylene oxide. So you have epoxide or ethylene oxide. Another name for it is oxyran. So you have oxyran, epoxide, or ethylene oxide. The name of ethylene oxide, it comes from the 2 carbon, that is ethylene, like 2 carbon alkene is ethylene, and then adding oxygen would be ethylene oxide. The reagent that you are using for epoxidation or formation of the epoxide, see what is needed from carbon-carbon double bond to go to the epoxide is addition of oxygen. This oxygen is coming from proxy acid. So proxy acid, let's say if you have proxy benzoic acid, you have benzoic acid. This is a formula for benzoic acid. Now, proxy benzoic acid, it has CO double bond O, then OH. Peroxide is an oxygen single bonded, just like hydrogen peroxide. Okay, very unstable. Just like if you buy a bottle of H2O, you keep it in brown bottle, you keep it away from heat, you keep it away from light. Otherwise, it's going to decompose and it changes to H2O plus O2. Okay, it bubbles or it decomposes and it will change to H2O and O2 because it's very unstable. With this, very similarly, the proxy acid, like this is a proxy benzoic acid, because of this peroxide is going to be very unstable. So this is going to help you to remember that if you want to make a peroxide, you do need an oxygen. And if proxy acid loses that oxygen, it's going to change to carboxylic acid, or if it's a proxy benzoic acid, would change to benzoic acid by losing that oxygen. That oxygen is needed to make the CC double bond change to epoxide or change to this oxyran. That's another name for it. The mechanism is like a more of an internal rearrangement. So the pair of electrons, it's going from the pi bond, is going to form bond, is used to be forming one of the bonds, and then oxygen brings one pair of electrons to form the second bond to form that epoxide. Very similar to formation of cyclopropane from carbene, but in this case, you're getting the oxygen from peroxy acid. Okay. I don't spend too much time on the mechanism for formation of the epoxide. So you don't have to worry about the formation of the epoxide, but ring opening of epoxide, you have to spend, we are going to spend more time on the ring opening of the epoxide. And then you need to know specifically like which carbon is going to take the nucleophile. Okay, so formation of the epoxide, what type of product are you going to get? Are you going to get a cis product or a trans product? When you have carbon-carbon double bond, cis and trans is applicable. In this case, you have two methyl group on the same side, so it's a cis reactant. When you do proxy, when you have the proxy acids with the proxy acids, you are going to add the oxygen to carbon-carbon double bond, and you get your cis oxygen or cis epoxide plus the benzoic acid. Metachloro proxy benzoic acid, MCP BA, that's a metachloro. That means there is a chlorine on the meta position with respect to this carbonyl group as the ortho position, and then this is a meta position, and across from it is going to be para position. So if it says MC, that's a metachloro proxy benzoic acid. So regardless if it's a meta or orthochloro, still that part is going to stay the same. So chloro doesn't change. The only change that we see here is the oxygen from the peroxy part is going to be removed, and it adds as a triangle or formation of a triangle to the carbon-carbon double bond, and it gives you epoxide. If you start with the trans reactant, trans alkene, you end up with trans epoxide. The ring opening, you should know from chapter 3 that when you have sp3 hybrid, this is the sp3 hybrid for each of these carbons, the bond angle, expected bond angle is 109.5. This is expected, but the actual is a 60 degree. So angle of strain here, it puts a lot of pressure in this this ring of epoxide. So epoxide ring can be opened easily if you bring in a nucleophile. So it can be attacked by a nucleophile. Why a nucleophile? Because oxygen has higher electronegativity, is going to pull electrons. So this carbon is going to be slightly positive. The other carbon is going to be slightly positive because electrons are pulled away from the carbons. So when you bring a nucleophile like H2O, you bring a nucleophile, the nucleophile is going to attack one of these carbons, and the ring is going to open. Why the ring needs to be open after you bring a nucleophile? Because the carbon here already has 4 bonds, right? You have 1 for CH3, 1 for hydrogen, 1 to oxygen, and 1 to the other carbon. Already has 4 bonds. You cannot force carbon with the 5th bond. So as soon as you bring a nucleophile to form bond with the carbon, because it has positive charge or partially positive charge, the ring is going to open. The ring will open, and then you can protonate the oxygen, and you have like a OH. So if you have the ring or the oxygen on top right here, water is going to come from the bottom. So the nucleophile is going to come from the opposite side of the ring. Basically, is like a back attack here. But the question is, if you bring the nucleophile, the nucleophile would the nucleophile go to carbon A or carbon B? Which one? Would the nucleophile go to A or go to B? Like in the case that you have a symmetrical, if you have a symmetrical alkene, is not going to make a huge difference. Both of them, it's similar. They both have similar or same positive charge or same magnitude of positive charge, and the nucleophile can go to either one of them. And is water strong enough to go and attack the epoxide? So those are two questions. If the water is not strong enough, what's going to happen? You have to protonate first. Use a catalyst. Like if you use a catalyst, you bring a proton first. If you acid catalyze it, we are going to change the epoxide to protonated epoxide first. So you bring in H plus here, you protonate the oxygen if it's acid catalyzed. Then the plus charge is going to be shared in here. So say you have like a CH3 and CH3 here. So this plus charge is going to come into the ring, basically. There is a plus charge in the ring, and the plus charge is not going to stay on the oxygen. It would be more on the carbons. And since both carbons, they have similar substitutions, or degree of substitution is the same, both of them are like a secondary carbon, then either one of them can be attacked by H2O. So when H2O comes in and form bond with, let's say, this carbon, then the ring is going to open over the OH. So the plus charge is going to be transferred. So now you have the plus charge in this carbon that is going to be shared between carbon and the oxygen. On the next step, you have to remove the plus charge. So to remove the plus charge, you remove one hydrogen with the plus charge, and the net result is formation of diol. So if it's a symmetrical, either one, the nucleophile can go either one. If it's asymmetrical, let's say if you have hydrogen on this side only, and you have carbon on the other side, if this is hydrogen and hydrogen, then water is not going to come here because plus charge is not going to be stable on this carbon. Plus charge is going to be more stable on highly substituted carbon. So then water is going to come and attack the nucleophile in general. In this case is water. It will attack the carbon that is more substituted, and then the ring would open. The OH would go to the other carbon, and then you have your H2O. Very similarly this with the plus charge, and you bring another molecule of H2O to remove the H plus. So the ring opening, if you do hydrolysis of epoxide, the final product is going to be diol. Okay. So the final product is going to be diol. You have OH and OH. And if you look at this molecule and say, I want to add water, so hydrolyze the epoxide, basically when you are adding water, you're adding H and you're adding OH. So one of these carbon-oxygen bond is going to break. This is not the mechanism, but it's overall reaction. H will add to oxygen, definitely, because oxygen is going to carry the negative charge, and then OH will add to the carbon. So you're adding H and you're adding OH, and the product is going to be diol. You have OH and you have OH. So formation of the diol is basically it's like a two-step reaction. First, you are going to start with the alkene. So from the alkene, you change that to epoxide. And then when you have the epoxide, you add water, you hydrolyze it, it changes to diol. And you notice that OHs, they are going to be on the opposite side. This is like anti-addition of the diol, or the diol is going to be on the opposite side, or it is anti. There is another reagent that can give you a cis diol, and that is treating alkene with osmium tetroxide in presence of H2O2. With osmium tetroxide, a bridge is going to form. And then just like hydroboration, when addition of H and OH, because there was a bridge in the mechanism part, then it was a syn addition. In this case, also the hint is that a bridge is going to form, or if you look at the structure for osmium tetroxide, the oxygens are going to be facing the two carbon, is going to be added from the same site. The final result is formation of a diol. So if you have osmium tetroxide with alkene, the final product is going to be diol. But the difference between this diol and the previous one, or for ring opening up epoxide, is that this diol or glycol is going to be syn addition. Both OHs are on the same site. But for the other one, from ring opening, the OHs are on the opposite side. So just that, if no, we talked about preparing flashcards. Like when you're preparing flashcards, when you're adding the osmium tetroxide, you also need to say that this product is going to be syn addition. The final product is formation of a diol, and it is a syn addition. That means both OHs are going to add from the same side of the molecule. Questions? Just make sure that you know the reagents, you know the product. Okay. Another method to make diol is dilute permanganate, reaction of permanganate with alkene. So if the condition is cold and dilute, so cold permanganate with aqueous permanganate, that means dilute, and it's cold, is going to give you diol. So you have the, you're going to have under the condition of cold permanganate. Okay, so it would be also added from the same site. So for cold permanganate, you're also getting the cis product added from the same site. If the permanganate that you're adding is hot, that means it's high temperature and is concentrated. So if it's dilute, it's like mild oxidation. If it's hot permanganate and is concentrated, so temperature is high and is concentrated, is going to cause like oxidative cleavage. What is oxidative cleavage? Meaning that it's going to cut through the carbon-carbon double bond, and that's cleavage part. And then we have oxidation, oxidative. That means it's going to add CO double bond or double bond oxygen to each side. So first of all, is going to cut or cleave the carbon-carbon double bond. Second is going to add double bond oxygen to each of the carbons. Now, if it's symmetrical, you would get two of the same product. If it's asymmetrical, you would get two different products. That part is kind of easy, of course, because you're cutting the molecule in half. If it's symmetrical, you would get one product. Second, if the carbon double bond, each one, if it's di or 2R carbon, means that both of the group attached to the carbon is alkyl group, your product is going to be ketone. If one is alkyl group, the other one is hydrogen, this product at the beginning, as soon as it cleaves off, is going to be aldehyde, but aldehyde in presence of KMnO4, because it's a strong oxidizing agent, aldehyde would change to carboxylic acid. So please pay attention that aldehyde intermediate is going to then go to carboxylic acid, okay? Aldehyde does not stay in aldehyde because hot permanganate is very strong oxidizing agent that will oxidize aldehyde to the next step, which is carboxylic acid. So what would you get here in this reaction? When you cleave it, so you have to make sure that you identify 2 carbon is attached to the double bond, or 1 carbon and 1 hydrogen. Like to the carbon on the left side, 2 carbon is attached because it's attached to a cyclic system. And then the carbon on the right, this carbon is attached to 1 carbon and 1 hydrogen. You don't have to write the hydrogen, but it's understood that a carbon has 4 bonds. If 3 is shown attached to other carbons, 1 must be hydrogen. So the left side of this molecule is going to give you ketone, and that's what we have, the ketone from the left side. From the right side, you would get aldehyde first, but since it's hot permanganate, it would change to carboxylic acid. And please pay attention to these final products. Final product is going to be, if it's aldehyde, would be carboxylic acid. But if it's ketone on both sides, it would stay as ketone. If the alkene is the cyclic alkene, okay, so is a cyclic, so you're going to get cleavage on the carbon-carbon double bond. There would be a cleavage on here, carbon-carbon double bond. Here you have only 1 carbon, so that is going to change to CO2. It's just 1 carbon, okay? But the other side, it would, because is attached to 2 other carbon, it will change to ketone. So you would end up with ketone. The carbon in the cyclic system, the carbon-carbon double bond cyclic system, if it's substituted, it can, like disubstituted, it would change to ketone. But if it's monosubstituted or just simple alkene in the cyclic system, is going to change to aldehyde, then carboxylic acid. Then it will change to the carboxylic acid. So you see there are a lot of changes that is happening in this molecule. The carbon double, you have 2 carbon-carbon double bond, both of them is going to be affected by the hot permanganate. You would have cleavage in both places. Here you get the CO2 because you just get like a formaldehyde, and then formaldehyde would oxidize to carbon dioxide. The carbon on top is attached to 2 other carbons, so it would stay as a ketone functional group from the cyclic system because there is 1 hydrogen. So like an understood hydrogen, you have hydrogen there. If there's a hydrogen attached to the carbon that carries the double bond, and you're adding hot permanganate, it will go to carboxylic acid. Okay. Let me know if you have any questions. I don't see any question posted in the chat. Please let me know if you have any questions. Another reagent for oxidative cleavage is ozonolysis. So you basically are using ozone. And with the ozonolysis, basically adding O3, if you add dimethyl sulfide, okay, dimethyl sulfide with the O3, with ozone, is a milder oxidizing agent compared to hot permanganate. So what this ozonolysis do is going to do oxidative cleavage, just like hot permanganate. This side of the molecule, because we have 2 R group, is going to give you ketone. The right side of that is going to give us aldehyde. If you had hot permanganate, aldehyde would change to carboxylic acid, but O3 in presence of dimethyl sulfide, it's milder oxidizing agent, the aldehyde would stay in aldehyde. So you get a ketone plus aldehyde. So in the organic like chemistry too, when you're preparing aldehyde, oxidative ozonolysis is one of the methods with the condition that you would use proper solvent. So what happens to this solvent here? Dimethyl sulfide is basically CH3, CH3, dimethyl sulfide. After gaining oxygen, you see, ozone has 3 oxygen. 1 oxygen would go to the right side, 1 oxygen to the left side, and the 3rd oxygen is going to basically oxidize the dimethyl sulfide, and with the oxidation of that is going to change to dimethyl sulfoxide. So you have some kind of reducing agent here, or a solvent that is going to remove the extra oxygen. So it kind of removes the strength of the oxidation power from the ozone, and ozone is not going to oxidize aldehyde. If you get aldehyde, it will remain as aldehyde. If you get 2 ketone, then you would have 2 ketone. So it's possible to have 2 ketone or 1 ketone and 1 aldehyde. But when you have hot permanganate, you could have 2 ketone, or if you have 1 ketone and 1 carboxylic acid, or you could have like 2 carboxylic acid. You cannot have aldehyde as a product of the oxidative cleavage using hot permanganate. Okay, so this is basically explaining why the aldehyde would stay as aldehyde, because the dimethyl sulfide is going to take the extra oxygen and would change to sulfoxide, DMSO, dimethyl sulfoxide. So when you were talking about DMSO or DMS in the chapter 7 or chapter 6 for SN1, SN2 reactions, that's basically what it is. You have the 2-methyl group attached to sulfur, that is DMS, and then DMSO is the oxygen also attached to sulfur. So it's the oxide, sulfoxide. You notice that there are a lot of reactions for chapter 8, and the only way you can survive next exam is to make sure that you have memorized all the reagents. Okay, all the reagents for chapter 8. Know the reactant, reagent, and product. Know about Markovnikov addition and anti-Markovnikov. Know about the Sasef rule or Hoffman product. Some of the addition reaction that is going to be syn addition or anti-addition. Make sure you have a flashcard for each one of the reactions with the specific condition. Okay. Last reaction from alkene is polymerization type reaction. In polymerization, your monomer is alkene. Alkene acts as a monomer, and then to generate polymer. You could have the mechanism of the reaction could be like acid catalyzed, and you get like a cation, or you could start with a free radical, or anion, a carbanion intermediate, which is not very, very popular. But regardless of the mechanism for the reaction, the polymer is basically repeating of the monomer unit. So if you start with like isobutylene, okay? Isobutylene, you have 4 carbon. Now this is like acid catalyzed. The first one is acid catalyzed. So you bring the proton, it would protonate one of these 2 carbons, and obviously the carbon with more hydrogen is going to take hydrogen. The other carbon would take the plus charge. So we have the plus charge here. Then second molecule of the monomer or isobutylene, we have plenty of these isobutylene in the reaction mixture, because this is the only reactant basically you have. Second molecule would attack this carbocation because you have a carbon-carbon double bond. The pi bond from it is going to form a new bond between a carbon from isobutylene and a carbon from carbocation. The other carbon will take the plus charge, then you have a new carbocation with positive charge on carbon number 4. If we always count from left to right. Now we have a carbocation, so we're just going to classify this as a carbocation, and the carbocation is going to be attacked by a third molecule of isobutylene, which is like here. The pi bond is going to be consumed to form a new bond between carbon from isobutylene and the carbocation that we had with 4 carbon. So when this new bond forms, it's going to bring the whole molecule together. Now we are going to get a carbocation that is like a larger size. We just added another 2 carbon to the main carbon chain. And we do have these methyl extensions. Every time you're getting a new bond, the methyl extensions are going to, every other carbon is going to have 2 methyl group on it. So this is a carbocation now. If we were going to continue, what would happen here is to bring another molecule of the, let's say CH2, and then you have like CH3 and CH3 here. A new bond is going to form from this pi bond is going to move between the carbon and the carbocation. A new bond would form, and this carbon would take the plus charge. So in every step, you're adding 2 carbon. This can continue over and over. That's why when you talk about polymer is a huge molecule, right? It's a long carbon chain, and depends on your monomer. If you didn't have these 2 methyl groups, it would be just carbon chain, like a polyethylene. Polyethylene is just a long carbon chain. There is no extension. So polypropylene, every other carbon has a methyl group, and then this is going to be polyisobutylene. Polyisobutylene is going to have every other carbon has 2 methyl group attached to it. But the idea is that in polymerization, you are going to have a large molecule, a long carbon chain, repeating the same, unit. So if you take any of these, like even if with just 6 carbon, if you take this molecule, you see you have the unit of isobutylene. This is the second unit of isobutylene, third unit of isobutylene, and then 4th unit of isobutylene, and it just continues like the link of a chain, and is going to be attached. It's going to form a polymer with the long carbon chain. What's going to happen to the last carbocation, that if it forms here and you want to stop the reaction, then you have to bring like an inhibitor. You have to have like a termination step. You have to bring something to stop the reaction. So if you bring another, like a base to remove a hydrogen, and it makes like a double bond, carbon-carbon double bond, like formation of alkene, because you have carbocation. let's say you want to bring a hydroxide. Hydroxide is going to react with this carbocation, and then it will stop. It doesn't generate another carbocation. So that would be like a termination step for polymerization. Sometimes like they add like inhibitor. Inhibitor acts opposite to enzyme or catalyst. It will actually slow down reaction or it will stop the reaction. So you can stop the reaction by bringing inhibitor, or if nothing, if you don't add anything, when all of the isobutyline is consumed entirely, then the carbocation is going to hit the wall and then stops. There's nothing else to do. The reaction will be done because there is no isobutylene left in the container. Polymerization can go through carbocation, it can go through free radical, or it can go through carbanion. And for carbocation, just know that you have to bring in. Remember, I said whenever you have like a peroxide, then the mechanism of the reaction would go through formation of free radical. And we were talking about like anti-Markovnikov when you have peroxide or alkyl peroxide or hydrogen peroxide. But in this case, at least know that you have a you have a free radical as the intermediate. But the mechanism of the reaction is going to be exact the same. The first free radical in the initial step is going to be attacked by the pi bond. Since only one electron is needed to form bond between the free radical and the first carbon, the other electron would move to the second carbon and gives you a free radical. So this reactant or monomer is called styrene. The product that is going to form is called polystyrene. So you have polyethylene, polyvinyl chloride. So different polymers. Beginning of chapter also we mentioned about the names for the polymers that you had. Okay. Any questions? Any questions from chapter 8? No?
So a good source to study all this is just from the slides alone.
The slides actually covers a lot of it, and it never underestimate the book. It doesn't replace the book. It does not replace the end of the chapter problem, but the PowerPoint covers a lot of